Um, welcome everyone to the Simons Institute. My name is Prasad Raghavendra. I'm the senior scientist at the Institute. The Institute was created in 2012 with a generous donation from the Simons Foundation, and we've been hosting programs, two programs every semester. And this semester we have a program on computational complexity of statistical inference, and this one on geometric methods and optimization and sampling. And this is the last workshop of the geometric methods and optimization sampling program. A few logistic things before we begin. So no snack or drinks inside the auditorium. There are lockers available to store your bags. Coffee will be served just outside the building. We have Ashia around. She'll be able to answer any questions you might have, logistic related. And Omid is helping us with the video. So this workshop on optimization, on symmetry, is organized by Nishit Vishnoi, Michael Walter, and Ashia Wilson. Thanks to NSF for the support of both the programs. And so without much ado, I'll let Nishit Vishnoi say a few words of introduction for the workshop. Nishit?
Yeah, hi.
Hey.
Can you hear me?
Yes.
Okay, thanks, Prasad, for this introduction, and thanks to the Simons Institute for their generosity allowing us to organize this workshop. I'm really glad to report with Michael Walter and Asia Wilson, my co-organizers, organizing this workshop titled Optimization Under Symmetry. Thanks to all of you who could make it and who are participating virtually from various parts of the world, despite very different time zones. So this workshop will focus on some of the recent trends that we have been witnessing in the design of optimization and sampling algorithms. In particular, once we hit a few non-convex optimization and sampling problems, it was realized that often non-convexity can be bypassed by using the underlying symmetries. And we will see several examples of this meta approach in this workshop, where once we realize that there is a symmetry group, typically a continuous symmetry group that acts on the objective function or the domain, then using and synthesizing techniques from geometry, algebra analysis, one can come up with some really new and interesting results, computational results. So this workshop will showcase problems and solutions from various domains, including theoretical computer science, discrete optimization, quantum physics, statistics, mathematics, and machine learning. And Melanie will be chairing the first session. So Melanie, it's over to you.
Okay. Is the sound system working? I think it is. Okay, great. Thanks everyone for coming, and I'm super grateful to be speaking here. Thanks Prasad and Nishith and Melanie. So I'm going to be talking about basically a cool connection between a problem that I've been working on for a long time, along with a bunch of my collaborators, norm minimization, with some other topics, in particular quantum tomography. And this is not really much of an optimization talk. It's more of a why might you care about this particular optimization problem, because of its neat connections to other things. So the first thing I'm going to talk about is just an example of quantum angular momentum. Then I'll talk about this connection between invariant theory and norm minimization, and also connection to tomography. And finally, I'll mention this proof outline of our kind of result, And in the proof, you can see that there's some relation between kind of a long-standing conjecture. We don't solve the conjecture or get anywhere close to it, but I think the connection is kind of promising. And then, of course, open directions. And there's also some closely, this is work with Michael Walter, I should have said. There's some very closely related work. Another group did essentially the same thing with very minor differences independently. Okay. So let's talk about angular momentum. So I'm not a quantum physicist by any means. If you are, please stop me and feel free to ask questions, although I might not know the answers. Okay, so imagine we have a bunch of copies of a quantum particle and it's some state. We don't necessarily know the state, but we have a bunch of copies of it. And we want to know if we measure the total angular momentum of this particle, what's the chance we get 0? Of this sort of ensemble of particles, what's the chance we get 0? Now, I don't know if you guys are familiar, but like quantum systems, it's not a deterministic thing, the angular momentum. If you measure it, you could get any number up to, the maximum angular momentum of a single particle, like times k. But in general, there's going to be some distribution. So for intuition, you could think of the classical analog. If you have a bunch of ±1 random variables, which are like weighted, probability p of +1, 1 minus p of -1, what's the chance that they sum to 0? This is a pretty easy problem. And you could think the connection is sort of that pluses spin up, minuses spin down. And there's like these turnoff bounds, which tell you pretty much exactly what, the rate of decay of this is happening. Like if p is exactly 0.5, then you get basically like 1 over root n or 1 over root k. I've omitted the polynomial factors here. I only care about the exponential ones. But if p is not 0.5, you get an exponential decay. Okay, and so the question is, depending on what the state is the probability of measuring angular momentum in the quantum case going to decay exponentially as well? And what's the rate of decay? So I'll tell you sort of the details or like the mathematical formalism of what's going on. It's not too important, for the rest of the talk if you understand all the details. But we think of a particle as a unit vector in some representation of the two-dimensional special unitary group. So that's 2 by 2 unitary matrices with determinant 1. And we write the action of the group element on the vector as g dot v. In the total angular momentum, as I said, it's going to be some random variable, Lk, because there's k copies. That's what the k stands for, and it's actually going to take half integral values. In the picture, I guess it's multiplied by Planck's constant, but here I'm just going to take it to be half integral. Okay, so here's what our result says for this problem. So it says that the limit of the chance of getting 0 raised to the 1 over k. The reason you raise to the 1 over k here is because you expect some exponential decay. So you want to know, like, what is this exponential rate of decay? Well, it's equal to a norm minimization problem over the 2 by 2 matrices with determinant 1. So I did kind of pull a fast one here. I said I had an SU2 representation, but I extended it to SL2. I need some kind of technical conditions to be able to do this, but basically all I need is that the representation I began with was, a polynomial representation. So think of it as just finite dimensional. Anyway, the point is you can express this rate of decay as this optimization problem. And this is just the Euclidean norm that you're optimizing over this group. So I think this is kind of neat. And one thing this immediately tells you, well, it tells you that you can compute this rate in polynomial time. This is a result of with a bunch of my collaborators. We work on this particular type of optimization problem, and I think it's probably going to appear a number of times in this workshop. It's called the norm minimization problem, and it happens to be geodesically convex in the right geometry, and you can efficiently compute it. You can't always. If this group here was, the dimension was growing, you can't necessarily compute it efficiently, but in this case you can. What else? Another thing you can say is that because the probability, the rate of decay is this number, the only way that it's going to concentrate at 0 is if this number is 1. So the only way it will concentrate at 0 is if this quantity is already minimized at the identity. And it's going to turn out that the gradient of this function at the identity will actually encode these expected directional angular momenta. So like the way it's going to work is that the only way you'll get concentration at 0 is if the expected angular momenta are 0 of your state. Okay. So it's like you have a random variable that morally has mean 0. That's the only situation it's going to concentrate. Okay. So for the rest of the talk, I'll tell you kind of the connections with invariant polynomials and norm minimization. I mean, this one's sort of obvious, but I think this connection is a lot less obvious, that you can express this probability as something about invariant polynomials. Okay, so I'm going to move on next to the invariant polynomials, and maybe I'll ask, do people have questions at this point? All right, let me check my time. I started early. Okay. So I guess we can, except for the group, that's the only thing that we need to kind of retain in our minds. We can clear everything from our minds. We're going to talk about invariance now. So we'll have G being some sort of nice group acting on a complex vector space. So basically always thinking about these very concrete groups here, the invertible matrices, that's GLN, SLN, invertible matrices with determinant 1, and products thereof. Technically, it's like complex reductive groups that we're going to worry about. Here's an example. You could have the invertible matrices acting on the space of n by n matrices by conjugation. So there's a good example. And there's this classical theorem of Hilbert, which says basically that 0 is going to be in the closure of an orbit, or is not in the closure of an orbit. That's called being semi-stable, just jargon. If and only if not every invariant polynomial vanishes on the point V. And if every polynomial vanishes on, invariant polynomial vanishes on V, then we say that V is in the null cone. Again, that's just sort of jargon for those who care about these kinds of problems. But this is sort of an intuitive thing. One direction of it is very easy. If 0 is in the orbit closure, then every homogeneous invariant polynomial must vanish on it, because these polynomials are continuous. So like they have to be 0 on this whole orbit because they're invariant. The cool thing about this theorem is that it goes both ways. So yeah, so this is just the sort of technical way of saying this. This is how we denote the degree k invariant polynomials. So they are preserved by this action. So I should just be careful and say, all that means is that if I have P, V here, and I plug in G, that's not going to change the value of the polynomial. Another way is that these polynomials take the same value across the group orbits. So what we were curious about, Michael and I, is whether there's a more quantitative version of this theorem, instead of just saying that, well, a point 0 is in the orbit closure if and only if there's no polynomials. What can you say about how far it is from the orbit closure and maybe how large these polynomials are? So one quantity we're going to care about is the distance between over the orbit closure to 0. And the other quantity is the magnitude of a random invariant polynomial. So we'll look at the expected value of its evaluation squared. And this is intentionally vague at this moment, but this is always going to denote, like, implicitly there's a degree around. So it's a random invariant of a certain degree. And I'll tell you how to actually draw it. But in your mind, you can, at this point, just think of it as like, an invariant, but with Gaussian coefficients. Okay. So this is the connection we're going to be looking at. And here's our result. We have that this magnitude of a random invariant evaluated on the point vector v is equal to the minimum squared distance to the orbit closure. So there's a pretty tight connection between these things. The only thing that I'm slightly lying about here is that really this should be a lim sup, because for some certain values of k, there aren't going to be any invariants. But all you need is that k just has to be divisible by a certain quantity. It's all the constraint on k is that it's divisible. So really this should be like k equals like a times L for some L that's going to infinity. But I've sort of swept that under the rug in the notation. Right, so I said I would say how to select this polynomial. Basically, this space, it's a vector space. So you could take like a complex Gaussian on it. Really, it's just any distribution that's isotropic. Doesn't really matter what it is. And the sense in which it should be isotropic is with respect to the Bombieri norm. And I will explain what that is, but it's actually just a super common and like very natural inner product on polynomials. And what about this norm? Well, I said it's just Euclidean, but you have to specify a basis for that. In general, it's going to be sort of an invariant inner product under some like compact subgroup. For example, if G was GLN, then it should be UN invariant inner product. But all the examples we're going to look at today, it's going to be obvious what it is. It's just going to be the Euclidean norm in some obvious basis. Yeah, so I said this already. Okay, any questions? So I'll talk a little bit more about the like why we care about these quantities. This minimal norm quantity has come up a bunch in my research and that of my collaborators. And we actually try to compute it in order to decide the vanishing of these invariants. And it's fortunate because, as I said, of this G convexity, you can compute it to arbitrary precision in a lot of cases. And some special cases, there's a lot of problems that sort of fall under this umbrella. Especially cool ones lately have been you can compute Braskamp-Lieb constants, so it's constants in some inequality and analysis, and it turns out that actually some likelihood functions in statistics turn out to be norm minimization problems too. And just a question, which I am curious about, is here we have some optimization problem, which tells us whether two particular orbits intersect. So it's whether the orbit of V and the orbit of 0 intersects. That's what this optimization problem here tells us. And what I'm wondering is, is there some analog if you have two arbitrary vectors, V and W? Can you write down some tractable optimization problem which tells you whether those orbits intersect? Because the orbit closure intersection problem is an interesting problem in its own right. And it's not it's not solved except for in the abelian case very recently. Okay. And I can just talk about the left-hand side a little bit. So what's this Bombieri norm? It's the way you define it is you just define it as an inner product, so that if you evaluate P on this like power of linear forms, like think of a tensor power of a vector as a polynomial, which means it's like a certain linear form raised to the k. You just make sure that P inner product with V tensor k is equal to the evaluation P of V. So it's really like if you have ever thought of polynomials of degree k as tensors, it's the natural inner product there. But it's not going to actually be important for understanding this. Okay, so another way to think about this quantity is just as an orthonormal basis of invariant polynomials evaluated on your vector V. So that's another way to kind of measure the size of the evaluations. It turns out they're the same. And another thing I should say is that don't use the formulas verbatim from this talk. I probably am missing, constants of dimensionality, but other than that, hopefully they're fine. Okay, another way to think of this is as an average over a compact group. You don't really need to worry about what K is, but I would just have this example in mind, GLN and the unitary group. So you can think of this quantity, the average value of an invariant of degree K, as a certain average of this quantity over the compact group. So like average of the unitary group. And that'll come up in the proof. All right. So here's kind of an interesting example in the abelian case. So maybe I think a lot of people here will have seen this matrix scaling problem. The group we're going to look at is the pairs of diagonal matrices with determinant 1. And they'll act on complex matrices by pre and post multiplication. And the question here usually is, can you choose X and Y to make A doubly stochastic, or at least proportional to a doubly stochastic matrix? It turns out that the, think about what the invariant polynomials are. They're going to be polynomials which, take in A as input. And all they are is the matching monomials, which is like, maybe A11, A22, but then you could have like A43, A34, so on. So the product of those things, like the monomials that show up in the determinant, right? So it turns out that for this particular degree, the expected value of the invariance of degree n is exactly the permanent of the matrix you get if you take the absolute value squared of all the entries. So the permanent is one of these things. And that's partly why I think that this is an interesting quantity, because it captures like neat things like permanent in it. And I'll just say that, well, that's just degree n. You can look at other higher degrees and you get these sort of higher permanents that Barvinach and Gervitz have talked about. Basically what they are is instead of, well, the permanent you could think of as summing up a matching monomial evaluated on a matrix. The higher permanents, you sum up polynomials where every monomial comes from a matrix where the row sums are all L and the column sums are all L. So it's like higher degree monomials. And our theorem says that the limit of these higher permanents is going to be equal to this matrix capacity, which is the optimization problem you try to solve when you try to make this matrix doubly stochastic. But I should say that in the abelian case, our theorem turns out to be the exact same thing as Sanoff's theorem on large deviations. And the right-hand side is just the dual of the minimum entropy problem that comes up in Sanoff's theorem. But I won't go into this connection much in the talk. Okay, yeah, and so I'll explain a little bit like why there should even be a probabilistic interpretation. So, okay. Before I go on, any questions?
All right. Question?
Yes.
So for the open question you mentioned,
Yeah.
is there any, maybe stupid to ask, but, or it's part of the question, is there any way of writing it as using, P1 of V and P2 of W, if you have V and W, and we want to know the intersection of the orbits?
Yeah, I mean, I would even use, you could even use the same invariant, right? Because it's like the orbit closures are going to intersect if and only if every invariant matches on those two vectors, right? So I feel like there should be something with, yeah, the difference between invariants on V and W. That's the question. All right. So now I'm going to explain why this quantity should be interpreted as a probability. So it's going to be the chance that some real valued random variable S is 0. So Rn, this n here is just going to be the dimension of the group we're looking at. Pretty much always for the rest of the talk, you can think of it as being GLN or SLN or maybe some products of that. And this letter S is going to stand for spectrum estimation, but I'll explain why that happens soon. So quick representation theory reminder, sticking to G being SLN or GLN, the degree D or degree K irreducible representations. So that just means that these are representations that don't break up further into direct sums of more representations. They are indexed by partitions, lambda, with K boxes and N rows. So this picture up in the corner, that's a picture of a partition with, I guess, 10 boxes and 3 rows. So partitions, think of them as just decreasing sequences of numbers of integers with some K. Each partition corresponds to a particular irreducible representation of SLN, and we're going to denote that V lambda. And one of the major classic results in representation theory is that any finite dimensional representation will break up into a direct sum of irreducible ones. So you can write this as a direct sum of irreducible representations of some V lambdas. And you can think of, imagine all copies of V lambda of a particular one corresponding to lambda. The direct sum of those copies is called the isotypic component of type lambda. So it's basically all the stuff that looks like V lambda in there. And we'll define this projection to be the orthonormal projection to the isotypic component of type lambda. So you start with the big tensor power or whatever, and then you project down to just the direct sum of copies of V lambda. So that's what pi k lambda is. And we can use this to define a random variable, S, the following way. So to parse this, first sort of ignore this part. This is just subtracting off some of the all ones vector. But this part is what's interesting. Basically, we're going to say S is equal to some normalized version of lambda with probability proportional to, actually equal to, the norm square of this projection. Okay, and why is this a probability distribution? Well, maybe I should have said, but V is going to be a unit vector. So if you have a bunch of projections which sum up to the identity, and you take the norm squared of their images and sum those up, that's going to be 1. These pi k lambdas are such a set of projections because the V tensor K breaks up into irreducible representations. And I won't go into the calculations or anything, but I'll tell you that the probability that S is 0 is exactly this random invariant quantity. And I mean, the reason for this is that if this is 0, that means that lambda, the partition, was just a big box, right? Because we're taking lambda and subtracting off the appropriate amount of the all ones vector. And it turns out that a big box, that representation is just the determinant. So it means that it's basically saying how much of V is projected down to the representation that's the determinant. And the reason that the determinant is sort of has to do with invariance is because we're looking at the group SLN, and SLN acts on the determinant trivially. Should it be lambda over N? No, it should be lambda over K, I think, because K is the degree. Okay, we could do a sanity check. So like if you have lambda being a box with right, each row would have K over N things in it. So you should get maybe this K shouldn't be here. Yeah, I apologize. So basically subtract off the appropriate amount of the all ones vector. Thanks for the question.
The combinations of boxes or something.
S is
So lambda is a box, is a shape. Or
yeah. Lambda, think of, lambda is just a vector in Rn. So it's like this one would be 5, 4, 1. Yeah. Oh yeah, so okay, so back to the angular momentum example, it turns out that S will be the random variable where you take the angular momentum and put it, negative in the first coordinate and positive in the second coordinate, and then divide by K. So in particular, S being 0 is the same as the angular momentum being 0. Okay, so yeah, I didn't just make this S thing up. It's a pretty well-studied thing. It's used in spectrum estimation in quantum mechanics. And it's called the empirical Young diagram measurement for a particular situation. So that situation is when GLN acts on matrices by left multiplication. So if A is a unit vector, meaning its Frobenius norm is 1, then rho is going to be a trace 1 PSD matrix. So we can think of it as a mixed quantum state. And it turns out that this random variable, Sk, converges in probability to the spectrum of rho. So the reason this matters is that given access to a bunch of copies of this mixed quantum state, which really means you have access to rho tensor K, you can sample from this random variable with one measurement of that K copies. So, otherwise, it's not clear, given a quantum state, how you measure it to determine whether it's pure state or not. So if it's, if it's a pure state, that means it just has, it's rank 1, it has one non-zero eigen value. The spectrum estimation measurement is basically the best way people know of, as far as I know, to figure out what the spectrum of the quantum state is. And there's a further refinement of this you can do. I'm calling another random variable t for tomography. Basically, once you draw S, you can draw another random variable u, which is going to be like some unitary matrix. And that's going to have the property that when you conjugate the the matrix with S on the diagonal by it, then actually that's going to converge to the state itself. So the moral of the story is that you can estimate not just the spectrum of the state, but actually the state itself from k copies of it. And actually it's known, some bounds for how well it works, and it works pretty well. Okay. Yeah, and I should just mention that T is kind of a quantum analog of just the empirical density function. If you had just a regular old probability distribution, how would you sort of estimate what the density was? Say it's like on just like n things, you would just keep sampling from it and then take the empirical distribution you got. That would be your estimate. So T is the quantum version of that. Why it has to be so complicated, I don't know, but that's how I think about it. Okay, so the question in this talk is, where do these random variables S and T converge for general representations, right? This spectrum estimation situation was just the very simple representation. It was invertible matrices acting on other matrices by multiplying. So you could have much more weird representations, like the example I mentioned at the beginning, just any particle, or the conjugation action, or so on. And we wonder where these random variables converge. So some people have done work on this before. As I said, the abelian case is just Sanoff's theorem on large deviations. Basically, that's because in the abelian case, T is just the empirical distribution function, and that's what Sanoff's theorem is about. And in terms of non-abelian stuff, some people have worked on this before. In the case that this mixed quantum state is the identity, in particular, Duffield solved this problem for arbitrary representations. And I should note that if the state is the identity, what this random variable S is going to be, it's just going to pick out a particular partition with probability proportional to the dimension of the isotypic component. So that's what Duffield actually did, is sort of figured out asymptotics for the dimensions of the isotypic components. And there's also a well-known result that if you take a random row, so sort of row corresponds to the vector v. If you take a random one, there's this measure called the Duistermaat-Heckman measure. And basically, they've already shown that this random variable S converges to this particular strange measure in that case. Okay, so before I tell you, so that's what we did in this work, is figured out where they converge in general. So I'll give some motivation for what that is. So what you might guess is that, well, we saw already that T is sort of concentrated around 0 if and only if the norm is already minimized at the identity. That was what I was saying at the very beginning. Because we already know that sort of if G dot V is minimized at the identity, then the rate of decay of the chance of getting 0 is 0. So it's basically very likely to be 0. So maybe you could hope that the gradient is where it's converging to, because if the gradient is 0, then it's sort of morally converging to 0. So it's not actually quite that simple, but it's really close. You just have to take some logs and put some exponentials in. So it's like, it's actually the geodesic gradient in this certain geometry. So I'm going to be using this quantity mu v. All you do is you take the gradient at 0 of the log norm of e to the h dot v. And this quantity is called the moment map in other literature. And a neat example is that, as I was saying, the gradient sort of encodes angular momentum. So in the angular momentum example, the moment map is going to be a 2x2 matrix, and it's going to be this linear combination of the Pauli matrices, where the coefficients are the expected angular momenta. So here's some more examples. So in the spectrum estimation case, the moment map is just the quantum state itself. And in the another example, if you have a product of 3 GLNs acting on a unit vector by tensor product, so G1, G2, G3 acts by G1 tensor G2 tensor G3 and so on, then the moment map is going to be the one body marginals of this quantum state rho. So I won't explain exactly what this is, but this is like the notation for tracing out part of the quantum state. So it's like if you have a quantum state that's shared between 3 people, Alice, Bob, and Carol, basically the marginals are the 3 things that what Alice sees, what Bob sees, and what Carol sees. Okay, so here's our result about this. We showed that the variable sk converges in probability to the spectrum of the moment map. So the moment map, remember, it's the gradient, and so it's going to be some matrix, and the moment map converges, or this variable s converges to the spectrum of it. And then this tomographic measurement converges actually to the moment map itself. And then, we can do a very similar thing to what we did in the first theorem, where we express any particular probability, limiting probability, as some norm minimization problem. But unfortunately, it's like a little bit complicated to write down what that problem is, but still, it immediately just tells you that it's sort of decidable to approximate this deterministically with any precision you want. And this picture is just sort of what the measure looks like if you this Doistermaat-Heckman measure, where if you select a row randomly. Okay, any questions about the results? Yeah.
So on 2 slides ago, I think, you had the first example of a geodesic gradient with the Pauli matrices. Yeah. Let's see. So what is the geometry there? That's SO3?
This is SU2. Is the group.
So this is the gradient along SU2?
It's actually, so you have, so SU2 is like, this is sort of this compact group. And then you have this bigger group, SL2, and this is where the optimization is happening. So we're looking at the this norm where this guy is in SL2. And it turns out you only need to bother looking at sort of positive semi-definite G. The reason is, this is the same as V G transpose G V, right? So you only need to sort of look at positive semi-definite G here. And the way we're going to parameterize this is just think of this as like e to the h. And we can choose h to be traceless. Trace h equals 0. So basically what we're looking at is the gradient for at h equals 0 along h being traceless 2 by 2. And then I guess I took a log. But in general, where you're going to be taking the gradient, that's a good question. Where the gradient is going to live, it lives in I times the Lie group, Lie algebra of this compact subgroup. So SU2 is going to be the traceless, the Lie algebra is the traceless anti-Hermitian matrices. So it turns out that, right, we're taking the gradient in the traceless Hermitian matrices. Sorry if that's a little confusing, but yeah, this is where
Where the I is the traceless thing. What's the I?
this I, yeah, this I, right, the way the moment map is defined over GLN, I should have said that this is the over the Hermitian matrices. So I turns the anti-Hermitian matrices into the Hermitian matrices. Yeah. Right. I mean, the way to think about this is like, you know, you can sort of move in both the you can move in the Lie K directions and you can move in the I Lie K directions. And the Lie K directions just rotate things. The I Lie K directions actually dilate stuff and make the norms smaller or larger. Thanks for the question. Anything else? Right. So the way we think about this is actually, it tells you the sample complexity of estimating the moment map itself. So the moment map is often kind of an interesting quantity, and our result tells you exactly what the asymptotics are for this sample complexity. You know, it's sort of weird that it's in terms of some optimization problem, which you don't have a closed form for, but that is the answer, so I can't do anything about that. Yeah, and I guess in quantum tomography, a lot of times people care about estimating only some certain linear functionals of the state. The moment map is an example of that. And you know, in shadow tomography, you hope to get a lot better sample complexity. So this is one way I think about this result. Yes.
So the sample complexity of estimating V of V, you're given V.
Right.
And you can compute or approximate mu of V using the algorithms now. So what, what do you mean exactly? What does the algorithm supposed to do instead?
Right. So I mean it in the like the sense of quantum information. So that's right. If you had V, it's how you're given access to V. So the way we access V, basically by taking quantum measurements. So you're not given V in terms of like, you're not given all the coordinates of all the entries. V is some unit vector in some vector space, and the only way you have access to it is to, take quantum measurements of it. So you sort of getting some noisy access to V. So the problem is about how you would estimate the moment map if you didn't really have access to V, you just had quantum access to it. I guess maybe one interesting use.
Capacity bounds are just used to, compute the rate of decay, the convergence.
That's right.
That's how you bound the number of samples.
Yeah.
You don't use the algorithm for
No.
just the bound.
That's right. Yeah. In order to get sort of results for decay, you would need to have some, reason that the capacity was sort of decaying around that point. Like you have mu, and you want to say that the probability of getting outside here is very small. You would need to have some bounds for why the capacity shrinks out here. Actually, we do have bounds like that. This is just the basically this. We have some bounds that say like the capacity of a vector v is less than some constant 1 minus some constant times the norm of the moment. So this basically says that you get some very concrete like rates of convergence for these estimators. And maybe one reason you might care is because in the algorithms for the norm minimization problem, you need access to this quantity mu. So if you only had, so maybe you wanted to run a quantum algorithm for minimizing the norm. Well, you would only have, access to the vector as a quantum state. So you could try to estimate it, as a quantum state, estimate mu, and then use mu in the algorithm. But I haven't sort of explored those things. Okay, other questions? Yeah.
So, how is spectrum estimation related to the angular momentum estimation? Is it a special case, angular momentum estimation, special case?
They're all special cases of this moment map estimation. They're just different special cases. So spectrum estimation is the case where you have V being, the n by n matrices. G is the general linear group, and the action is, G dot some matrix A is just GA. So in that case, the moment map is actually just A transpose. And this is how you were parameterizing the state you were. Basically, the angular momentum problem is just any time that your group is SU2. Very well. So I won't talk too much about the proofs, but I'll give a quick sketch. So I'm going to sweep a lot of the pre-processing under the rug. So this is the inequality we want to prove, remember. I'll just say that it's enough to prove this whenever the right-hand side is equal to 1 and the vector that you started with is equal to 1, which means that the right-hand side is already minimized and this gradient, the moment map, is equal to 0. The reason for this is because these quantities are both sort of invariant under the group action. The left-hand part is invariant because all these polynomials are invariant. The right-hand part is invariant because if you act on V by some vector, by some group element, then you can change variables. So you can sort of move things around until the moment map is 0. Okay. And we just need to show that mu V being 0 implies that this limit is equal to 1. So what that means is that you need to show that if the moment map is 0, you are getting a bunch of, you have many invariants, which are substantially large on that vector. Yeah. And the proof of this is kind of like the Fourier analytic proof of the local central limit theorem, in the sense that we're going to be just looking at some interval. So we're going to use this formula which I already mentioned, which is that it's equal to some average over the unitary group. And we need to show that this is decreasing not too fast. So a 1 over poly k lower bound will suffice, because remember, we're taking this all to the 1 over k at the end. And what we're going to do is, I guess you could call it the stationary phase approximation. We're going to show that for a Hermitian matrix H, right, you can write down any unitary matrix as e to the IH. And we're just going to show that for, sorry, this should say H approximately 0. Probably just a typo. For H being close to 0, this thing looks like a Gaussian. And then in the end, you can estimate the integral for H nu 0, which means u close to the identity, by some Gaussian integral. And you can just totally write down what that quantity is, and it satisfies this. And then you show that for u far from the identity, this is just small. So v inner product with u dot v is less than 0.9. And when you raise that to the k, that's going to decay exponentially. And then this, unitary group, well, the whole volume of it is finite. So this, if this were to work, it would be enough. Of course, modulo a bunch of details. And it turns out that this thing is not really going to be true. You might have some directions you can go in the unitary group that fix v, the vector. So if once you mod out by those, you sort of replace this by modding out by the stabilizer of the vector, then this proof strategy works. Okay, questions about this proof idea? It's actually not very hard.
Zero come in? Is it getting the stationary phase?
That's right. It's here. Because basically if you took the Taylor expansion of this, like the first order stuff, that would be the moment match. Yeah. All right. So I just want to mention a connection to a conjecture. It's called the Mathieu conjecture, and Mathieu conjectured it because it implies this Jacobian conjecture, which I'll talk about in a minute. But what this conjecture says is that it looks at a very similar quantity. It's the only difference is that you have two different vectors here. And it says that if this quantity vanishes for all k, then also for any other two vectors, for all but finitely many k, this quantity also vanishes. Okay, so I admit that this doesn't look very meaningful. Doesn't look very meaningful to me, at least. But it implies this other conjecture, which is sort of neat and old, that if a polynomial function on the complex vector space has constant non-zero Jacobian determinant, it has a polynomial inverse. And I think that the connection is basically that, we proved that if v equals w, we basically proved a formula for this. This is just because of that formula I mentioned, that this random variant is equal to this average of the unitary group. So we proved a formula. But if you plug in two different vectors, our proof breaks down, and I don't know what this is. And this is the quantity that they care about in the Mathieu conjecture. So what I wonder is there a way to characterize this quantity? Maybe it's like what the gentleman over there mentioned, that it has to do with the differences between invariants or something like that. And in the abelian case, the Mathieu conjecture has been proved, and they used a formula a lot like this. So what I'm hoping is that this function f of v and w has something to do with the distances between the orbit closures of these two different vectors. But no, I don't know. I don't really have anything in this direction. I just think it's cool. Okay. Yeah, questions about this previous slide? This one, yes.
It's like the group is a bit.
Yeah, the group is a bit. Yeah. Sorry. Yes. This is the conjecture.
You could still maybe from your proof, start with V, with W, with V, and then move the conjecture of V prime.
Yeah, actually, it's the Mathieu conjecture in the V equal W case is true, and it's like you don't end up needing the formula in that case. It's like it actually has to do with the moment polytopes. Yeah.
Do you get anything useful if you just try to write this inner product to the power k down in terms of the entries that you and grind out the Weingarten calculus?
I actually don't know what the Weingarten calculus is.
This is there's a general machinery for computing expectation values of polynomials in the entries of the unitary matrix with respect to the Harmonian.
I think that's what people do to get special cases of this conjecture. So I think it's maybe been, okay, I saw a paper that was looking at it over SU2, and they didn't prove it, but they said like, it's promising because of these calculations or something.
We don't know how to really do Weingarten calculus on SU2. We only know how to do it on UN with that.
Okay.
With that circle.
I see. Well, seems like maybe a good idea. Yeah.
So you stated this conjecture for UN and also the abelian groups. So what is the general setup here?
Yeah. So the general conjecture is actually that you're supposed to be able to plug in any. The general setup is the following thing. It's like you have some nice group G, which I mentioned it needs to be like some reductive group, so SLN or something like that. Yeah, it's a complex connected. It's going to act like algebraically on the vector space V. And then you have this group K subgroup, which is like a maximal compact subgroup. So you could replace UN with this maximal compact subgroup K, and that's the generality that the conjecture is in. But I think it's not known for already these interesting cases, but smaller cases. Okay. Yeah. So open questions. Michael and I are actually looking at this a bit right now. Is that we have formulae for the rate of decay of this random variable. So basically, how well it's concentrated. So these are like kind of like turn-off bounds. But you could hope for sort of much finer control in the range where the moment map is on the order of root k. So you could hope it like decays Gaussianly there. There are quantum local central limit theorems, but as far as I know, they don't. They're very different looking. So that would be something to look into. And obviously, as I was saying, you want to understand this Mathieu conjecture. And another thing, which I'll mention, is that sort of we gave large deviation principles for this event, that this tomographic measurement was equal to a particular thing, but it wasn't in terms of entropy minimization problems. It was in terms of norm minimization. So one thing I've wondered for a long time is there some sort of relative entropy-like thing between maybe vectors, or maybe you need to put the quantum states here or something, where the rate of decay is equal to the least relative entropy of some vector W, such that the moment map is the right thing. But I don't know of such a thing. Yes, it does. That's why it's equal to, or like that happens from the connection with Stanoff's theorem in the abelian case. Yeah. It's also like this thing in matrix scaling where this capacity, which is this problem you solve to get doubly stochastic scalings is also equal to like an entropy minimization problem. Okay, I think that's it. Thanks.
One minute, so anybody. And the next talk will be in half an hour.